What would life be like on a planet in a binary system? Could it be better? Or is planet Earth really as good as it gets?
If you're looking for an abode for life in the galaxy, we tend to, look for a rather cozy existence out there, but, it's possible that stars can take you on a bit of a wild ride sometimes.
Over the past decade, we've observed mysterious objects hurtling through the galaxy. Scientists call them hypervelocity stars.
When we say hypervelocity stars, we're talking some hypervelocities. They've been observed moving up to 620 miles per second.
You're talking about something the size of a star, the sun, an octillion tons of mass or something like that, getting flung away way faster than a rifle bullet.
These hypervelocity stars start off in a binary system, but something tears them apart, something big.
In order to create a hypervelocity star, you need a very intense source of gravitational power. Well, the most intense source we know of is the black hole at the center of the galaxy.
This black hole is Sagittarius A star. It's supermassive, 4 million times the mass of our sun. Two stars stray a little too close, and the enormous gravity of the black hole pulls at them. But the star closest feels a much stronger tug, and this binary system gets ripped apart.
It's a little bit like the Olympic hammer throw, where the hammer is one star in the binary system and the Olympian is the other star, with the cord connecting the hammer being the gravitational tie between the binary stars. If you cut that cord, the other star can go flying off at very, very high speed.
Once the cord is cut, the binary stars separate forever. One is trapped in the gravitational grip of the black hole. The other is flung out of the galaxy, becoming a literal shooting star. But the star may not be alone.
If a planet is gravitationally bound to a star, and that star gets ejected from the system, if conditions are right, that planet can hitch a ride with that star. Where the star goes, the planet goes.
If you were on a planet around a hypervelocity star, you would be the envy of poets and scientists everywhere because you would have the most breathtaking view imaginable. You would start at the very center of the galaxy, you would have this beautiful view of the supermassive black hole.
Generation after generation on this hypervelocity planet would be treated to thrilling new views of the galaxy.
By the time you're done, as you're ejected, you would see the entire Milky Way galaxy, everything, and it would recede away from you as you moved off into space to who knows where.
Hypervelocity planets just go to show that the universe is way stranger than fiction.
As we learn more about stars and stellar systems, even the most fantastical imaginings of sci-fi writers, it doesn't even come close to what nature can produce.
This hypervelocity star and planet go on the journey of a lifetime. But what about the stranded companion star, stuck in the center of the galaxy, next to a supermassive black hole? It too could have a planet orbiting it. But it's a world living on borrowed time.
If there's a planet orbiting the star that gets left behind by the hypervelocity star, so the planet is now orbiting the star that's orbiting the black hole, that's not probably going to last very long. Typically, the little guy gets shot away. So it's entirely possible that we have hypervelocity rogue planets, planets without a star that are shooting out of the galaxy at high speed as well.
But it's not a trip you'd want to take. Because this world is destined to wander through the emptiness of space forever, alone.
The problem with a planet is that it's no longer bound to a star, so the outer surface would most likely freeze.
Binary stars create weird environments for planets. You could get an exhilarating view of the galaxy, or you could freeze on an icy wasteland. But astronomers are finding bizarre new systems where stars are not being torn apart, but being driven together, creating a cosmic event coming soon to our galaxy. For life to conquer the universe, first, it has to get going.
When we look at life on Earth, it's possible that it all has a common ancestor. Life started at one spot, branched out, and became all the different kinds of life that we see.
But how did it start? The first question to answer is, what is life made of? Top of the list are the most basic building blocks, chemical elements.
Here's what I know about the universe. The laws of physics appear to be the same everywhere. The chemical composition, the elements, are the same everywhere.
And the cosmos creates these elements not from the Big Bang, but from stars.
Over the course of a star's life, it creates elements. And when a star dies, these elements are blasted out into space in a supernova, spreading the ingredients for life out into the cosmos.
We, the Earth, our solar system, all the ingredients that make us us were forged in nuclear fires. So the death of stars leads to the birth of life.
Those key ingredients include oxygen, nitrogen, sulfur, and phosphorus. But the element most central to life as we know it is carbon.
All life as we know it on Earth is based on carbon.
Carbon forms the structure, the architecture of our living molecules.
Carbon is an incredibly versatile building material. It can bond with other elements to form long-chain molecules, each with different properties.
As an element, it seems to be capable of producing a vast and complex chemistry. And that complex chemistry is what we find in life.
We call this organic chemistry. But getting from basic organic molecules to complex life forms is a big leap.
We don't really have the slightest idea, to be honest, about how life on Earth got started.
A really big question is how you go from a mix of relatively simple organic molecules to a living system.
We know it all starts with basic elements, created in massive quantities by the death of stars.
But how do you start connecting those Lego bricks together to build that first cell?
The short answer is we don't know. But we have some ideas of potential steps.
Chains of organic molecules become more and more complex. Amino acids form proteins. Fatty acids form phospholipids, which make cell membranes. Nucleic acids form DNA, the molecule that stores genetic information. Eventually, a simple cell emerges.
All of the bits you need to plug together to build a cell from scratch seems to exist in outer space.
We found organic compounds everywhere. They're all over the place. planets, comets, gas clouds.
The very basic ingredients of life available elsewhere in our solar system. So there could be life everywhere.
In 2018, NASA announces it's found organic molecules on another planet. A planet we've always suspected of harboring alien life. Mars.
So whenever NASA has a press conference and they say they have some important results to report on about Mars, everyone goes nuts.
The internet goes mad. Maybe we've got photographic evidence of little green men in an UFO.
This time, it's the Martians. They're gonna tell us they found the Martians.
The world listens because everyone wants to know. Everyone asks the question, have we found evidence of life?
For 6 years, the Mars Curiosity rover has been exploring a region called Gale Crater, hunting for signs of ancient life. A bit like fossil hunting on Earth.
Gale Crater is not unlike places on Earth that can preserve fossils. So a really good example of this would be the petrified forest in Arizona. This looks like a piece of wood, but in fact, it is stone. It is all stone. But it used to be a tree. This fossil lived 200 million years ago.
This patch of desert in Arizona once looked completely different.
This landscape looks very dry right now, but 200 million years ago, it was wet swampland with trees and flowing water.
Like the petrified forest, Mars has also changed over time. Gale Crater was once a lake bed filled with fresh water.
And it was just so exciting because we knew then that we had landed right on top of an environment that once had tons of flowing water and could very well have preserved organic materials, even though it looks very barren and desolate to our eyes.
In 2018, Curiosity drills into this ancient Martian lake and discovers organic molecules.
Finding organics on Mars is so exciting just because, I mean, wow, those are the building blocks of life, not just the elements, but actual molecules.
There was a wave of excitement after the announcement of organics found on Mars and complex organics. It's not totally indicative that life is there, but it's a really good telltale sign that there may be possibly life forms on Mars.
The results aren't proof of Martians, but the ancient lake bed is evidence that the red planet once had something else crucial for life: liquid water.
It's one thing if you have all these ingredients lying around for life. You could have, carbon over here and hydrogen over here, maybe methane or whatever. But you have to mix them together. So you need something for them to be in, a medium of some sort.
Life needs a liquid to mix essential chemicals together. We're used to thinking of Earth as the only water world in our solar system. But new evidence says otherwise. As extraterrestrial visitors carrying liquid water from outer space reveal. In 2017, astronomers tried to solve a decades-old cosmic mystery. Unexplained high-energy radiation streaming through our galaxy. At first, we didn't know where it was from. But we discovered it was gamma radiation coming from somewhere in the center of the Milky Way.
The question is, what's making these gamma rays? That's hard to do. It's not like you can rub your hands together and generate gamma rays.
When we took a closer look at the gamma rays, we discovered the signature of the most explosive substance in the universe: antimatter.
Antimatter is like normal matter, but with opposite charge. That's it. It's matter's evil twin.
When evil twin meets good twin, it is not a happy reunion.
Antimatter is scary. It's not like you want to have some in your kitchen. This stuff is very, very explosive if you want to think of it that way. If it touches normal matter, it releases a huge amount of energy.
When matter and antimatter combine, they annihilate each other and transform into high-energy radiation, just like the gamma rays seen streaming out of the center of the Milky Way. We see antimatter throughout the galaxy, but strangely, the galactic center seemed to have 40% more antimatter than anywhere else.
Right now, in the heart of our galaxy, we actually observe fountains of antimatter that are producing 10 trillion tons of antimatter every second.
One of the big questions that we've wondered about for a very long time is, what's the origin of this stuff?
Initially, there were several suspects.
One possible source of antimatter is the central supermassive black hole, Sagittarius A star. Matter can be swirling around this, and it can have such high energy that it can create antimatter.
But the antimatter isn't coming from a single point. It's spread across thousands of light years of space. So Sagittarius A star can't be the source of the gamma ray stream. Another suspect was dark matter.
One of the biggest mysteries in the universe right now is dark matter. We know that the majority of mass in the universe is not in the same form that we are. It's not made of atoms. But whatever sort of particle it is or may be, if these things collide, they can produce antimatter, and that will produce the gamma rays. So it's possible that as we look into the heart of the galaxy and see these extra gamma rays, that's the signal that dark matter is there.
But the gamma ray stream we detected is too weak to have been created by dark matter. Then, we had a breakthrough. We discovered that a special metal called titanium-44 could be responsible for the gamma ray stream.
Titanium-44 is a highly radioactive element. That means that it wants to decay into other types of nuclei.
When titanium-44 decays, it gives off antimatter. But to produce the antimatter seen in the galaxy's core, you would need a lot of titanium-44. It could be created in rare energetic events. In the collision of two dead stars, white dwarfs.
A white dwarf star is a star that didn't have enough mass when it died to actually become a supernova. It just sort of cools off as a dead little cinder. But what if you have two white dwarfs that are orbiting around each other? And as they come closer and closer and collide, all of a sudden now you have enough mass to actually kick a supernova explosion off. These particular kinds of supernovae are very good at producing titanium-44. So these kinds of supernovas are very, very good at making antimatter.
These supernovas erupt in the core of the galaxy once every 2,000 years. But outside of the core, in the disk of the galaxy where our solar system orbits, these supernovas happen 3 times as often. So the gamma ray observations were wrong. There isn't more antimatter in the heart of the galaxy. It's our region of the galaxy that contains the most antimatter. The question is, are we in danger?
If you take an ounce of matter and an ounce of antimatter and collide them, you're generating a megaton of energy, the equivalent of 1,000,000 tons of TNT exploding. So you don't need much antimatter to generate a vast amount of energy.
But the thing you have to remember is we live in this wonderful, dramatic environment of the larger universe. It's not dangerous. It's very far away from us, and it's fascinating. that all of this antimatter is being produced in our galaxy. So just sit back and enjoy the fireworks.
The center of the Milky Way is violent and extreme, but things could get a whole lot worse. Rogue, supermassive black holes could be lurking near our galaxy, and they have the power to end life as we know it. Earth has orbited the Sun for over 4.5 billion years. Time enough for humankind to evolve into an intelligent and technologically advanced species. But compared to the age of the universe, planet Earth is just a kid.
The Earth is over 4.5 billion years old, and we think it's taken this long to create the first technological civilization, us. There are star systems out there much older than we are. The universe is 13.8 billion years old.
We tend to think we're hot stuff, right? We're technologically capable, we can build rockets and we can listen to radio waves. But a typical other intelligent advanced civilization would be literally millions of years ahead of us in technology.
So if an alien society has been around longer than us, how much more technologically advanced could they be? One method of measuring just how much is provided by the Kardashev scale.
The Kardashev scale classifies potential alien civilizations into 3 types based on the amount of energy that they're able to harness from their local environment. A Type 1 civilization can harness the energy of only its home planet. A Type 2 could hypothetically harness the energy of its own solar system. And a Type 3 could harness the energy potentially of an entire galaxy.
If you're wondering where we fit on that scale, prepare for some bad news.
We're somewhere between a 0 and a 1. We can't use all of Earth's resources, so we're at about a 0.7.
An advanced species reaching Kardashev level 2 or even 3 could create highly advanced structures that can harness the power of a star.
If you get to be an advanced enough civilization, eventually, if your energy demands are so huge, you might build solar panels that you have enveloped your star. This was first thought of by Freeman Dyson, and so we call these Dyson spheres.
If such epic engineering occurs in other star systems, or even other galaxies, could we pick up some evidence and then make first contact?
The thing about a Dyson sphere is that you've completely blocked all the light coming out from a star, except for the infrared, because these panels are absorbing that sunlight and warming up. When you warm up an object, it gives off what's called thermal infrared light. You can scan the skies looking for that signature to see if there are any Dyson spheres out there.
2015. NASA's Wide Field Infrared Survey Explorer scanned 100,000 nearby galaxies to locate advanced Kardashev civilizations by observing infrared light leaking away from Dyson spheres. They detected nothing.
No such galaxy was found, so they didn't find any infrared smoking gun.
Given our universe is so old, surely other civilizations should have had time to evolve. If so, maybe we've simply missed them.
It's entirely possible that civilizations arose, tried to communicate with the galaxy around them, and the problem was they were asking too early for us. They're trying to knock on our door, but our house wasn't built yet.
Earth has been around for under 1/3 of the universe's 13.8 billion year lifespan. The human race, just 300,000 years. A relatively tiny window of opportunity to make first contact.
We've been looking at the sky for tens of years, something like that. What is the likelihood that at that exact moment, someone is going to be beaming a signal toward us?
Perhaps the universe prevents intelligent civilizations from surviving for very long, making our chances for first contact even more unlikely.
Maybe there is something out there that is filtering us from seeing them. We actually call this the Great Filter. Maybe there is something that says, yeah, you're not getting past here.
Rocky planets like ours are ideal for hosting life, but they're fragile. And this fragility means the universe could filter out intelligent life quickly.
We've discovered very violent star explosions like gamma ray bursts. And these are powerful enough they may sterilize planets, even across an entire galaxy.
And even if intelligent species survive natural phenomenon, they may still be filtered out by hitting the self-destruct button.
As we can tell from our own experience, the moment that we started developing technology, we also developed the means for our own destruction by changing the climate on our planet, by developing weapons of mass destruction. And so it's quite possible that civilizations that are advanced enough are short-lived. And if they are short-lived, that would explain why at this point in time there are very few of them that might be around to communicate with us.
Finding the relics of an extinct alien civilization could be the ultimate cosmic warning for the human race.
If we were to find a civilization out there that may have destroyed themselves by pollution or conflict, it would be almost like staring into a mirror, and it would be a very grim foreshadowing and maybe a lessons learned for us humans here on Earth.
We can only hope that some advanced alien species escaped the universe's deadly filter. But even if ET still exists out there, the odds are still stacked against first contact.
One other way that we've got this alien contact story a bit wrong is just down to the laws of physics.
Every day, the physics of the cosmos makes our chances of contact worse because our universe is expanding, and it's expanding fast. February 2018. Astrophysicists at the University of Oklahoma find a potential series of rogue planets 3.8 billion light-years away. Ranging between the size of our moon and Jupiter, these would be the first alien worlds ever discovered outside our galaxy. And maybe the first of many.
Our galaxy alone has trillions of planets. The observable universe has trillions of galaxies. It's estimated about 2 trillion. So trillions of trillions? Come on.
But finding exoplanets is no guarantee of finding alien life. And when it comes to contacting extraterrestrials, our efforts have met with silence.
Our search for life has come up empty. Do we need to change our tactics? Are we doing something wrong?
I think it's going to be very, very hard to find extraterrestrial intelligence the way that we're looking for it. We would have to get really, really lucky. But I don't think we're going to get lucky. I think that if we want to know whether there's life out there in the cosmos, we have to go visit it.
We find the microcosmos in every feature of Earth. But where did this strange kingdom of the very small come from? Some of its members are so weird, they look like aliens. Could they have come from space?
There's this idea that microbes could have hitched a ride on a chunk of an asteroid that would fall to Earth.
They could form on a different planet, something hits that planet, the rock that they're sitting on gets lifted, and then hits the Earth as a meteorite.
The idea of hitchhiking bugs sounds a bit wild. But we have found chunks of Mars on Earth. Perhaps these space rocks brought life.
It's not completely ridiculous. We know that rocks, for example, could come from Mars and land on Earth. A giant asteroid impact on Mars could blow shrapnel into space that could land on Earth.
To learn how, we must return to the early solar system, 4.5 billion years ago. Many infant planets orbit a new star, our Sun. This infant solar system is chaotic. Collisions between planets are inevitable.
The early solar system was like a pinball machine. Stuff was hitting, knocking stuff off, that would land somewhere, knock stuff off.
The young Mars is in the line of fire. It already has primitive oceans, and perhaps primitive life. A huge space rock smashes into the surface. We call the event the Borealis Impact. It blows quadrillion tons of rock into space.
It's not crazy to think that one of these chunks of rock traveling through our solar system has some hitchhikers on board.
If there's some microbe riding on an asteroid that got blasted off of Mars, kind of feel sorry for it, right? It's just living there on Mars, doing whatever little Martian microbes do, and then a giant impact ejects this thing into space.
In order to get from one planet to another, a cell would have to run a gauntlet. It's almost like winning a survival game show. You've got to survive being blasted off your homeworld. You've then got to survive the interplanetary journey inside a small lump of rock, being exposed to the vacuum of outer space, to cosmic rays, to UV radiation, being dried out and frozen.
So the idea of moving life around the solar system or around the galaxy on asteroids poses a lot of different challenges.
Events like the Borealis Impact ejected so much rock from Mars, there were lots of opportunities for hitchhiking bugs to run the gauntlet of space. But could they survive the journey? To find out, astronauts on the International Space Station grew simple bacteria outside in space.
After a year of being in open space, miraculously, some of these microbes survived. It's incredible. These microbes just could not be killed, even though they were in the worst possible environment for life.
The mission, therefore, shows us that life can survive the environment in outer space. Life can be transferred between planets. Maybe life did get started on Mars and our next-door neighbor planet, and then was transferred here inside a meteorite. Maybe we are immigrants from Mars.
Hitchhiking bugs may have arrived on Earth and kick-started the microcosmos. But now, recent studies of meteorites suggest that even if living microbes didn't make the journey, the building blocks that made them did. In November 2019, an international research team found an organic molecule called ribose in meteorites that had crashed on Earth.
Ribose is a sugar. It's a simple sugar, but it is a sugar that is absolutely crucial to all life on Earth. Ribose is the sugar that makes up RNA. And RNA sits right in the linchpin of every cell.
RNA is a simple form of genetic material that controls cellular function. It's found in most primitive creatures.
Finding ribose on a meteorite is so important for us to understand the origins of the microcosmos, because these are the building blocks. These are the things that it needs to get started. So understanding where these building blocks come from allows us to understand how the microcosmos might have evolved and started.
The Rosetta mission found another building block for life out in space, a form of phosphorus on the comet 67P.
This was astounding. Comet 67P was formed at the birth of the solar system, 4.67 billion years ago, and it hasn't changed since then. It's a time capsule from the birth of the sun and the planets.
And it's been in the deep freeze ever since. So these forms of phosphorus that we found on Comet 67P tell us what was available at the time the Earth was forming, and then when life was getting started on primordial Earth.
The early solar system contained many chemicals needed for life.
It's an important discovery because it means that these compounds were around when the solar system was forming. So they would have been readily available for life to tap into and use to start forming cellular structure.
These discoveries not only show that essential chemicals came to Earth, but that they exist throughout the solar system.
We tend to think of the microcosmos as only existing on Earth in the sense that only Earth has these building blocks, but now these new observations suggest that a microcosmos, at least the building blocks for one, could exist beyond Earth and throughout the solar system.
Comets and asteroids may have brought chemicals to kickstart the microcosmos. Now, explosive new research suggests that space rocks hitting Earth did even more. Could the violent impacts themselves have helped life get started? We've discovered some extraordinary exoplanets. Superhot worlds with molten iron rain. Super puff planets, so fragile they might blow away. Exoplanets that defy physics. But stranger still is the case of the disappearing planet. Over a decade ago, the Hubble telescope spotted a planet orbiting Fomalhaut, one of the brightest stars in the night sky.
Fomalhaut is a very nearby, very young star, and the images of this system are incredible because what you see is the central star surrounded by a bright ring. It looks just like the Eye of Sauron.
We observed the new planet, called Fomalhaut B, for 6 years. Then, something surprising happened.
All of a sudden, it just wasn't there anymore. Where did this planet go?
For it to suddenly be gone, it was amazing. It was astounding. It was terrifying.
If Fomalhaut B can suddenly vanish, what could that mean for other planets and us?
We live on a planet, so we have a vested interest in understanding how planets could disappear if that's a phenomenon that exists.
October 2019. Astronomers investigate the idea of a vanishing planet by looking at BD plus 20307, a star system straight out of the movies.
Just like that iconic image from Star Wars, from Tatooine, where you look up and there's 2 stars in the sky, that's actually not that crazy.
Out there in the wild, wild west of the universe, you have lots of different kinds of star systems. In fact, it's more common to have pairs of stars orbiting each other than have stars by themselves.
If 2 star systems are the norm, what makes BD plus 20307 different? The 2 stars lie within a bright disk of gas and dust, like Fomalhaut. But Fomalhaut is a young system, less than 500 million years old. BD plus 20307 is 1 billion years old. And that's weird, because the material in the disk is so old, it should have formed new planets long ago. So what's going on?
Rings of dust are a characteristic of young planetary systems. What does it mean when we see a disk of material surrounding an older star, a star over 1 billion years old? Well, one thing could be the collisions of planets. We think that in this system, planets collided, and that formed the disk that we see.
When planets collide, they don't just spew out masses of material. The violence of the event shakes up the whole planetary neighborhood.
Planetary objects come in with such energy and such speed that essentially they are vaporizing each other.
Observing a planet essentially being destroyed tells us something about what might happen in our own solar system. Our planets feel very stable in their orbits, but we don't realize that in the future, those orbits might be very different than they are today.
Early in its existence, our solar system was a demolition derby with many, many collisions. It's how rocky planets like ours formed.
Back then, there were more than 8 or 9 planets in our solar system. There were hundreds, and planets were running into each other and interacting with each other all the time.
Eventually, the planets we see today formed, and our solar system settled into a nice, regular arrangement. Finding strange systems like BD plus 20307 makes us question that narrative.
One of the really valuable lessons that astronomers have learned from studying planets around other stars is that it appears very clear now that planets don't necessarily stay where they are in a solar system.
Over time, the orbits of planets in our solar system slowly shift. The repercussions of these orbital fluctuations could shatter our cosmic neighborhood. The odds are slim, but billions of years from now, Mercury could be pulled out of its orbit by gravitational interactions with Jupiter. This action would set Mercury on a fateful course.
One potential future that our solar system may have is actually that Mercury could collide with Earth, which sounds crazy, but would also be a real bummer.
So what we see in BD plus 20-307 is theoretically possible in our own solar system.
It's actually been a bit of a wake-up call. It's a transformation in our understanding of how our solar system works.
Studying other systems shows us just how vulnerable planets can be.
Things can change at any time in a planetary system. That we could be watching a planet on its orbit one day and poof, it could suffer that really big collision the next.
But could this all explain the case of the Fomalhaut B system? Could it have collided with another planet, wiping it out completely?
Well, maybe. April 2020. Astronomers at the University of Arizona come up with a new theory about Fomalhaut.
Every good mystery needs a shocking twist at the end. And the twist in this tale could be that the planet disappeared before Hubble's eyes because it never was there to begin with.
Instead of a planet that we thought we captured inside the ring, it was actually a collision between two smaller objects called planetesimals.
Planetesimals are infant planets. Bodies that measure from a few miles to hundreds of miles across.
They smashed together and created a huge dust cloud, which we caught with Hubble. All we saw was a bright blob of light that looked like a planet.
They didn't spot a planet, but they did learn a very important lesson.
We're actually observing a process, part of the way that solar systems grow and are born. And in many ways, that's, I think, more important and more useful to us than having spotted yet another planet.
Exoplanets are opening our eyes to the way the universe works. We must question some long-held assumptions. One standard text predicts the sun will eventually engulf the Earth. But could there be a way out? Do some planets cheat death? Galaxies are vast kingdoms of stars. Some are giant balls, and others complex spirals. Thing is, they never stop changing.
While it may seem when we look out at our galaxy that our galaxy is static and been here forever, it's not. Our galaxy is a dynamic place. Its very nature has been changing over cosmic time.
Galaxies not only change, they move as well. And sometimes they run into each other. And when they do, it's eat or be eaten.
There's a zoo of galaxies that you can find out there, and this entire zoo can interact or collide with any of the other members of the zoo.
This is NGC 2207. It looks like an enormous double spiral galaxy, but it's actually two galaxies colliding. The collision will last millions of years, and eventually the two galaxies will become one. Collisions like this happen all over the universe. Our own Milky Way is no exception.
The Milky Way is in fact a cannibal, and it exists in its present form by having cannibalized small galaxies that it literally ate up. And today we can see small streams of stars that are left over from the most recent mergers that have formed the Milky Way galaxy.
But that's nothing compared to what's coming up. We are on a collision course with the galaxy Andromeda. And for the Milky Way, that's bad news.
Our Milky Way galaxy is approaching Andromeda at the rate of about 250,000 miles per hour, which means that in 5 to 6 billion years, it's all over for the Milky Way galaxy.
You would see the entire Andromeda galaxy speeding towards us, really barreling straight into us. As the two galaxies interact, they both become more and more disturbed and closer together, and the whole process starts to snowball.
The two galaxies will enter a death dance.
This is a simulation of the future collision, sped up millions of times. As the galaxies crash together, clouds of gas and dust are thrown out in all directions. Gravity from the merging galaxies rips stars from their orbits and shoots them deep into space.
As we approach doomsday for the Milky Way galaxy, it would be spectacular. We would have a front row seat on the destruction of our own galaxy. Eventually, the two galaxies will go right through each other and then come back and then coalesce.
It's strange, but the stars themselves won't collide. They're still too far apart.
All of the stars are basically just going to pass right by each other. The probability of one individual star hitting another individual star are basically zero.
However, the gas and dust between the stars will start to heat up. Eventually, it ignites, and the clashing galaxies will glow white hot.
So at a certain point, the sky could be on fire.
The Milky Way and Andromeda as we know it will cease to exist, and Milkomeda will be born, and it will look like a whole new galaxy.
This new galaxy, Milkomeda, will become a huge elliptical galaxy without any arms or spiral shape. There's no escaping what's going to happen. The question is, what's it mean for planet Earth?
We may either be thrown out into outer space when the arms of the Milky Way galaxy are ripped apart, or we could wind up in the stomach of this new galaxy.
Stars and planets will be pushed all over the place. So, this may well be the end of planet Earth. Galaxies all over the universe will continue to collide. But this age of galactic cannibalism will eventually pass. Because there is an even more destructive force in the universe, a force that nothing can stop. It will ultimately push galaxies away from each other, stretching everything until the universe rips itself apart. Our moon, like a lot of moons, is rocky, barren, and pockmarked with craters. But in one way, our moon is unique in the solar system. For a long time, astronomers thought the moon formed from debris left over from the birth of the Earth. But researchers in the 1960s came up with a radically different idea. They suggested it came from a giant impact.
When we first had the idea of forming the moon from a giant impact, that was not a terribly popular idea. And I actually did have good science friends, colleagues coming to me saying, you know, we really have to exhaust all the slow evolutionary theories before we start talking about cataclysms.
The evidence Bill Hartmann needed was on the moon itself. And the proof had to wait until Apollo astronauts finally went there in 1969. They brought back hundreds of pounds of moon rocks. Scientists analyzed the rocks and were amazed. They were identical to rocks in the Earth's crust, and they'd been superheated. So how did pieces of the Earth's crust become super hot and wind up on the moon? Hartmann was pretty sure he knew.
This whole idea was that the Earth forms, now you hit it with something, you blow all this light rocky material off the top, that material goes into orbit and makes the moon. The moon's just made out of rocky debris.
Imagine our chaotic solar system 4.5 billion years ago. The young Earth is just one of 100 or so new planets orbiting the Sun. One of them is a Mars-sized planet called Theia, and it's on a collision course with Earth. They smash into each other at many thousands of miles an hour. Theia is destroyed, and Earth barely survives. The impact blasts billions of tons of debris into space. The Earth's gravity pulls it into orbit around the planet. Now, these hunks of leftover Earth clump together and form our moon. That's the theory, anyway. But how do you test it for real? Here at NASA's Vertical Gun Range, they're recreating that ancient collision in a lab. This 30-foot-long gun fires a tiny projectile at 18,000 miles an hour. The projectile is Theia. This ball represents the Earth. By changing the angle of Theia's impact, the team can figure out how precise the ancient collision had to be in order to make the moon. In the first shot, Theia hits the top of the Earth with a glancing blow.
So here's the Earth, if you will, just suspended in space, and now it's gotten hit. So now we see the planet, the ejecta, is being ripped out of the Earth and is forming this giant impact basin. And if this really were the Earth, this basin would be thousands of kilometers, thousands of miles across.
In this simulation, Theia only skims off the surface of the planet, and very little debris is thrown out into space. Not nearly enough to build our moon. The second shot is a head-on collision.
That's the end of planet Earth. It's gone. Some of the debris is going to go out of the solar system. Some of the debris will reaccrete to form small planetesimals within the solar system.
There's no Earth left, so there's no gravity to gather the debris and form the moon. Now, the gun is set to just the right angle, halfway between a glancing blow and a direct hit.
So we'll see what happens if the Earth barely survives. Oh, gorgeous. Oh my gosh, kapow! Now we have the entire part of the Earth being ripped apart, but the vapor plume is, oh my gosh. Ah, jeez, that is gorgeous. But this was the beginning of our moon.
The experiment shows that Theia could have smashed into the Earth and formed the moon. But the collision had to be just right, and lucky for us, it was. Today, the moon orbits 250,000 miles from Earth. But when it first formed, the moon orbited just 15,000 miles above the Earth's surface.
500 million years after the moon formed, if we looked up in the sky, the moon would have comprised a tremendous portion of the sky. It would have been enormous because the moon would have been much closer.
Back then, the Earth was rotating so fast, a day lasted just 6 hours. But the moon was so close, its gravity acted like a brake. It slowed our planet down until a day now lasts 24 hours. The moon's gravity also created giant tides that surged across the planet, churning up the seas, mixing minerals and nutrients. This created the primordial soup from which the first forms of life arose. Without our moon, life on Earth may never have happened. And there may be other moons with a link to life as well. Moons may be the great biology experiments of the universe, the true laboratories of life itself.
The planets of the solar system grew from a giant disk of dust and gas. The 4 inner rocky planets close to the Sun, and the giant gas planets further out. But Uranus and Neptune seem out of place. There wasn't enough material this far from the Sun to make such big planets. So why are they out here?
That led us to a theory where Uranus and Neptune formed very close to the Sun and were actually violently pushed outward.
But what could move 2 massive planets clear across the solar system?
We believe that Jupiter and Saturn got into this funny configuration where Jupiter went around the Sun exactly twice, every time Saturn went around once. And that configuration allows the planets to kick each other more as they pass one another. And that caused the whole system to go nuts.
The combined gravity of Jupiter and Saturn pulled hard on Uranus and Neptune and dragged them away from the Sun. As they moved outward, the 2 planets crashed through asteroids and other debris left over from the formation of the other planets. This sent billions of chunks of rock flying in all directions. Some rocks formed the asteroid belt, but most were thrown out to create the vast Kuiper belt.
The analogy I like to use is think of a bowling match. And the bowling balls go down and the pins just go kaplooey. That's what happened in the outer part of the solar system.
But the gravitational push from Jupiter and Saturn was so strong, it may have reversed the position of the two planets.
Looks like it's possible that Uranus and Neptune actually formed in the opposite order. Neptune was closer to the Sun than Uranus, but these gravitational interactions actually swapped their positions.
The blizzard of rocks that Uranus and Neptune ran into acted like a brake and slowed them into the orbits they keep today. While Uranus and Neptune stabilized in their new orbits, a swarm of comets and asteroids rained down on the inner planets, bringing with them a precious cargo. The asteroids carried water from the solar system's outer reaches. Without the movement of Uranus and Neptune, and the shower of asteroids, water might never have reached Earth. Then there would have been no oceans and no life. Evidence of this bombardment can still be seen today, but not on Earth. When astronauts examined craters on the Moon, they found that most formed at the same time, 3.9 billion years ago, the time of the Great Bombardment. The idea of planets changing orbits may sound far-fetched, but scientists have seen it happen in other solar systems, and they now think it's just the way all solar systems work.
When we look out into the galaxy and look at planets around other stars, we see lots of evidence of those kind of events happening elsewhere.
In one far-off system, scientists have seen something quite extraordinary. A planet as big as Jupiter, but it's not acting like the Jupiter we know.
Some of these giant planets are found orbiting very close to their host star, taking only days, a few days, to go around the host star. Obviously, such close-in Jupiters are blowtorched by the star, raising the temperature of the planet up to 1,000 or 2,000 degrees Celsius.
A gas giant could not have formed this close to the Sun. It's way too hot. The only explanation is that it must have formed out there and then moved in here. An identical thing could have happened in our own solar system. Scientists have found large amounts of the element lithium on the surface of the Sun. Lithium doesn't normally exist in stars, but it is found in gas planets. Perhaps there was another gas giant in our own solar system that crashed into the Sun. This would explain how the lithium got there. Ours is not the only solar system in the Milky Way galaxy, and most of the others seem strange in comparison. As we've seen, some planets follow unusual orbits, while some smash into each other. Others dive into their stars. So why are the orbits of our own planets so regular and stable?
Well, that's because all the planets have motion left over from the formation of the solar system. When the nebula collapsed around the Sun as the Sun was forming, there was an intrinsic motion, and that gave our planet a velocity. Literally, we are falling freely toward the Sun at all times, but we're going so fast we keep missing it. That's what an orbit is.
It's similar to a merry-go-round. The faster it spins, the further and further you're thrown from the center. And when it slows down, you lose momentum and fall back inwards. It's similar to this with planets. The disk that gave birth to the planets was spinning, and the momentum left over from that keeps everything going around to this day. Moving at 107,000 kilometers an hour, the Earth takes 1 year to orbit the Sun. Planets further from the Sun have bigger orbits, move slower, and take longer. Saturn orbits the Sun once every 29 years. Neptune takes 164 years. Each planet stays on a precise path around the Sun, which is good for us.
Our solar system has a somewhat fortunate spacing of the planets with nearly circular orbits, which keeps the whole house of cards from falling apart, crumbling, scattering to the wind. If our solar system did not have nice, neat, stable, nearly circular orbits, the Earth wouldn't be here, and we wouldn't be here talking about it.
The planets are on safe, stable orbits. But billions of comets and asteroids are not. Many come streaking into the inner solar system, and when they do, Earth's in jeopardy.
Meteor crater, which we see here today, formed as a result of a 150-foot rocky iron object coming in and slamming into the Earth roughly 50,000 years ago.
Some of the objects on a collision course can be much bigger. Look at the Moon. It's covered with large impact craters. Earth has been hit too, a lot. But these craters have eroded. We know that a huge asteroid smashed into the Earth off the coast of Mexico 65 million years ago. It was traveling at 72,000 kilometers an hour, and when it hit, it released more energy than 5 billion atomic bombs. It wiped out 70% of life on Earth. A few more impacts similar to that could destroy all life on Earth. But, believe it or not, Earth has a giant protector.
Jupiter is more than just another pretty face through the telescope. It's actually really important for life on Earth. Jupiter's gravity is so huge, and it's just in the right place in the solar system, that it protects the Earth from comets that come from deep in the solar system and swing by the Sun and could possibly hit the Earth.
Jupiter plays the role of the biggest baseball bat in the solar system. As these comets come by, most of them get knocked out of the solar system by Jupiter.
In 1994, comet Shoemaker-Levy 9 raced towards the inner solar system, but it never got past Jupiter. Astronomers watched as Jupiter tore it to pieces and dragged its remains down to the planet's surface.
We have seen comets smash into Jupiter, creating fireballs that were bigger than the Earth.
They were the biggest explosions ever seen in our solar system.
Had that comet hit us, it would have resurfaced the planet. It would have been the end of life as we know it.
If Jupiter wasn't there, we believe that the impact rate on the Earth would be something like 1,000 times more than we see today.
We're extremely fortunate, as Earth has the perfect orbit. Jupiter protects us from asteroids and comets. We're close enough to the Sun for liquid water, but not too close that it boils away. It's just the right combination for life. The question is, if our solar system could create the perfect conditions, could it occur in other solar systems too? Planet hunters have spotted a solar system 20 light-years away, and there is a planet just the right size and in just the right place.
Take a look at the night sky. We now know that planets probably surround almost every point of light you see. But there's more. For every star we can see, there are countless others too dim for our eyes to pick out. These are the red dwarfs, far smaller than the Sun, but home to planets by the truckload. And many of these worlds are made from rock, like the Earth.
There are more red dwarfs than any other kind of star in the galaxy, and these stars have planets too. So the most common type of planet in our galaxy is one that lives around a red dwarf.
Of the billions of red dwarfs in the Milky Way, more than 1 in 20 have planets that orbit at just the right distance for liquid water to collect on the surface. Any closer, the temperature would be too hot and the surface water would boil. Any farther away, and the water would freeze. It's often called the Goldilocks zone because it's just right for oceans to form, just as they did on the Earth. Could one of these warm, wet worlds provide a habitat for life like us?
That's kind of the holy grail of this whole thing, to find something that looks like home. For one thing, that means that it could have life on it. It could be habitable. And that's something that we've always wanted to know the answer to. Are we alone?
These rocky, wet planets may seem like dead ringers for the Earth, but there's a catch. Many red dwarf worlds orbit so closely to their dim host stars that the same side of the planet would always face inwards, held in place forever by the star's immense gravity. Scientists call this phenomenon tidal locking.
We're all familiar with the fact that the Earth spins on its axis and gives us night and day. But if you move in closer to a star, eventually the gravitational interaction will stop that rotation. One side of the planet will always face the star, one side will always face away, and you're tidally locked.
If you land on this planet and look around, you're going to see stuff that's very different depending on where you are. If you're on the point on the planet that is underneath the star, so that when you look up, that star is straight up, that's where it's always going to be. It never rises, it never sets, it never moves. That's where the star is. Now, if you're on the other side of the planet, it's always nighttime. You look up, you never see your host star in the sky.
In 2016, astronomers discovered a potentially Earth-like planet orbiting the Sun's closest neighboring star, Proxima Centauri. The planet, dubbed Proxima b, sits close enough to its host to have oceans like the Earth, but scientists suspect it's tidally locked. The result, Proxima b may be staring at its parent star like a giant eyeball. The night side is a dark, frozen wilderness. The day side, a sun-blasted desert. But between the two lies hope for life. A long, thin strip of land in permanent dusk wraps around the planet like a ribbon. J.D. Radabaugh pictures an eerie twilight zone where dark glaciers melt to fill vast lagoons, just as Earth's glaciers do during the summer.
The boundary between these two completely different landscapes is something like what we're sitting on right now. Basically, we would have liquid water flowing off of these glaciers, pouring off the glaciers and heading out into the wasteland. And icebergs calving off into this beautiful bay. We've got liquid water, we've got energy from this burning sun, and so this is exactly the kind of place where we would look for life.
A ring of hope for life on a planet orbiting the sun's nearest neighbor. Could Proxima b really be home to alien civilizations? Until we go there, the jury's out. But red dwarfs burn for trillions of years, and they outnumber the other stars in the sky 3-to-1. If advanced alien civilizations really are out there, the planets of red dwarf stars could be ideal places to find them.
Let's say that we were sitting on a planet around one of these red dwarfs, maybe 1 trillion years from now. We could still be sitting here. We've never seen a red dwarf die. And so if that's true, then there's plenty of time for life to have gotten started. So not only do we have microbial life, but maybe even more complex life, and then take it a step further, we might even have intelligent life in these locations.
It's amazing that even tiny stars can have potentially habitable rocky planets, no matter how weird these worlds may turn out to be. But when astronomers turn their telescopes to bigger stars, the surprises keep coming. These sun-sized stars have planets too, and some of them could be the weirdest yet. Imagine a gas planet so black, it appears to be eating light.
If an alien astronomer were to file a report on our home solar system, they might make a surprising observation. Because of all the 8 planets that orbit the Sun, they could easily conclude that 2, not 1, were suitable for life. It's an easy mistake to make, because the Sun has 2 planets within its Goldilocks zone, the Earth and Mars. Both planets have surfaces warm enough for liquid water to pool on. But while the Earth is blessed with warm, liquid oceans, Mars is dry and dead. The one crucial difference between these 2 planets could be the key to finding truly habitable exoplanets: a magnetic shield. Our Sun is constantly hurling deadly radiation out towards us. Only our magnetic shield, the magnetosphere, saves us. Without it, the solar wind would blow our atmosphere away, and without an atmosphere, liquid water could not exist on the surface.
In order to have liquid water, not only do you need the right temperature, but you need the right pressure. You know, if there were no atmosphere here right now, even at the same temperature we are today, all of the water would boil off into vapor immediately.
So where does the Earth's magnetosphere come from? And why doesn't Mars have one? Actually, in the past, both Earth and Mars had magnetospheres, but Mars lost its around 4 billion years ago, and with it, the potential for life. Both the Earth and Mars were born into a realm of violence. Asteroids smashed into their surfaces, turning rock and metal into a molten mass. As they started to cool, a solid crust formed on the surface. But the molten metal below churned as the planets turned, inducing a magnetic field which rose high up above the surface of both planets. At the same time, active volcanoes pumped gas into the space around each planet. Protected by the newly formed magnetic field, these gases built up into thick atmospheres, creating the air pressure for liquid water to run on the surface. For over 100 million years, both Mars and Earth were warm, wet paradises, primed for life to take off. Then, quite suddenly, Mars's magnetic protection disappeared. The solar wind blew its atmosphere into space, and its oceans boiled away, leaving the dry, sterile red rock we see today.
Mars' fundamental problem is that it's smaller than Earth. And because it's smaller, the internal core of Mars cooled down and solidified. And once it becomes a solid metal, there's no more magnetic field. The magnetic field shuts off, essentially, and the atmosphere, therefore, is vulnerable to both energy and radiation from the sun and the rest of the galaxy, and probably just blew off. Whatever life was on there, at least on the surface, is now completely exposed.
All rocky planets will one day lose their magnetospheres as their cores cool and turn solid. So, to know if an exoplanet is alive, you need to work out if its magnetosphere is still active. But magnetospheres are tough to measure because they are unbelievably weak.
The Earth has a magnetic field of approximately half a Gauss, which, when you think about it, is actually really weak. Our fridge magnets are about 100 Gauss, so they're much stronger.
Exoplanets are too far away for us to measure such weak magnetic fields directly. But there is an indirect method. When electrons in the solar wind interact with a planet's magnetosphere, they emit radio waves that beam out into space, turning the planet into a giant radio beacon. Astronomers like Evgenia hope to use these signals to spot habitable exoplanets. Not only that, the frequency of the signal should also tell her how big the planet is.
If we're looking for the magnetic signature in the radio waves of a giant planet, say a hot Jupiter, we expect it to have a strong magnetic field, and therefore it would have a high frequency, and around 100 megahertz, kind of where the limit of this radio is. However, a weaker field like Earth's requires us to go down to lower and lower frequencies. So instead of 100 megahertz, we go down to 10 megahertz.
But hunting for exoplanets at 10 megahertz presents a unique challenge. Because the Earth's own magnetosphere creates a deafening radio roar at that frequency. So to find alien Earths using radio requires a dish in space.
When we want to look for magnetospheres of extrasolar planets, we really need to get outside of the Earth-Moon system in order to get away from all the radio frequencies that are bouncing around the Earth.
With a slew of new technologies and upcoming technologies, scientists are edging ever closer to the ultimate prize, finding a second Earth.
I wouldn't be surprised if we have that data about an Earth and about life on it around another star in 10 or 15 years. I'm hoping to see that soon.
Using shadows, rainbows, and now radio, we finally have the tools to detect a planet just like our own. But in the rush to find the Earth's identical twin, are we missing something big? What if Earth is an outlier, a freakishly lucky place on the very fringes of habitability? Could there be another kind of planet out there, even better for life?